He is going to talk about properly embedded minimal annuli in H2 cross R.
Thank you very much. Well, first of all, I would like to thank the organizers for the kind invitation to participate in this colloquium. It's my first time here in IMPA. And I'm going to talk about a joint work with Leonor Ferrer and Magdalena Rodriguez from Granada and Rafe Maceo from Stanford. And I'm going to speak about minimal annuli like this one in the picture. I mean, minimal properly embedded, minimal annuli in H2 cross R, so that the ends of the annuli are horizontal or vertical graphs. I mean, the boundary at infinity, well, in this case, well, this is known as a catenoid in H2 cross R, and the boundary consists of two parallel cycles in the ideal boundary of H2 cross R. And this is the idea. The ideal boundary of this annuli consists of a pair of vertical graphs over the circumference at infinity in the hyperbolic plane. Well, just to fix some notation, I'm going to use along all the talk the Poincaré disk model with the usual metric. And so the product metric in H2 cross R is given by this metric, and I'm going to refer the ideal boundary of H2, in this case, corresponds to the complex numbers of modulus 1, so this unit sphere in the complex plane. So as I'm going to use and abuse about what is called hyperbolic dilations in H2, I would like to explain what I mean by this. So I consider in the hyperbolic disk a geodesic gamma. Then, so the hyperbolic dilation by ratio lambda greater than 0 consists of moving along the equidistant curves from gamma the same ratio lambda in all these equidistant curves. That gives you a rigid motion of the hyperbolic planes that I'm going to call dilation of ratio lambda, or ratio in this case is in the slide is S. Okay, so and I'm not going to distinguish when you consider this horizontal rigid motion in the in the Poincaré disk that induces rigid motion in H2 cross R, just making the product with the identity in the third coordinate. And I'm not going to distinguish between this motion and this one. I'm going to use the same notation for both. Okay, so what are the simple examples of embedded minimal surfaces in this product? So the first one are the total geodesic planes, horizontal slice, or what I'm going to call vertical planes that consist of the product of a geodesic eta times R. And something which is not so trivial is these examples that I'm going also to use due to Ricardo Sayarp and Eric Toubiana, that well, I'm going to call tall rectangles. And well, so they prove in a very nice paper that if you consider two parallel pieces of arc of circumferences, joined by vertical segments in such a way that the height is greater than pi, then it's possible to find an area minimizing properly embedded disk, like the one in the picture, which has this property. It's area minimizing, which is even more than being minimal. Area minimizing in this context is a complete minimal surface. It means that any compact piece is area minimizing. So it's followed by equidistant curves. What is the meaning of that? That means that, well, if you see this picture from above, so the piece of the arc of circumference is something like that. So there is a unique geodesic joining these 2 points. I call it sigma. And then you have the equidistant curves to this geodesic. So being followed by equidistant curves, that means that the horizontal sections of this disk here are equidistant curves to that geodesic sigma. Well, using these examples are important because very recently, Baris Koskunuser used these examples as a barrier to prove the following. Imagine that you have a curve, a tall curve. I'm going to explain in a minute what's the meaning of this. In the ideal boundary of H2 cross R, then there exists an area minimizing surface sigma, so that the boundary of sigma, the ideal boundary, is this curve gamma. Well, the meaning of tall is the following. You consider this curve gamma in the ideal boundary of H2 cross R. Tall means that the interior of gamma is, which is a subset in the ideal boundary, is simply connected. And that given a point in the interior, x, there exists, for any point, there exists a segment, vertical segment of length bigger than pi, included in the domain, in the interior of gamma. This is the meaning of a tall curve. And well, the idea of Koskunuser is a nice idea, but well, it's also very standard. He constructed this example sigma as limit of solutions of compact plateau problems. The problem of this construction, so he considered compact curves so that the limit at infinity is this curve gamma. But the problem of this construction is that the solution of the plateau problem can disappear at infinity when you take limit as this sequence of curves go to gamma. So he uses these examples of Sayar and Toubiana and this fact that you always have at this segment. So that means that you can place here a small tall rectangle containing the point x. And this gives you a barrier to prevent that the limit of the sequence disappear at infinity. Okay, so the next example, non-trivial example, is this family of catenoids of revolution. Well, the idea of the construction is the same as you can have in R3. I think it was Euler in the 18th century who proved that. As you impose that the minimal surface is a surface of revolution, and then you reduce the PDE to an ODE. That, well, in this case, is not as easy to integrate. So because the parametrization is given in terms of Riemann elliptic functions. But this family, so if you see, now the ideal boundary at infinity consists of two parallel cycles. And so I'm going to call h the height. So you can see in the construction that this example exists only for h between 0, the distance between the boundary cycles goes from 0 to pi. So pi is a magic number in this theory. And it has this behavior. When the height goes to 0, then it's like in the Euclidean case. So the limit consists of two totally geodesic disks, or a double totally geodesic disk with a puncture at the origin. Where the convergence is not smooth at this point. When the height goes to pi, the limit consists of, or disappears at infinity. So the limit is the cylinder at infinity between 0 and pi. So you don't have a limit, properly speaking, in H2 cross R. You have limit in the compactification. And the slope of these catenoids at the boundary, the slope is monotonically increasing as a function of h, well, from 0 to plus infinity. Okay, so in particular, this example in the picture corresponds to the middle one, the one in the middle, where the height is precisely pi over 2, just for completeness. And you can play as, this example is also very interesting, because you have that this family, when pi goes, when the height goes to pi, disappears at infinity. But you can play a double game in the sense that you can push using these horizontal dilations the neck of the catenoid to the origin, so that you force the neck pass through the origin at the same time that you move the height to pi. And then you get a limit. And the limit is what is called this generalized catenoid that was discovered independently by Benoit Daniel and Laurent Hauswirth, and has the property that is foliated by horocycles in parallel planes. So now, well, this example is not an annulus anymore. In the compactification, it's an annulus, but in H2 cross R, it's a disk. And the ideal boundary consists of a cycle at height pi, a cycle at height 0, and a vertical segment that you can appreciate in the picture, connecting the two cycles. Okay, we have these two characterizations that I'm going to use. The first one is due to Nelly, Barbara Nelly, Sayarp, and Toubiana. They proved that a minimal annulus bounded by two parallel cycles must be as to a hyperbolic dilation one of these catenoids. And the other characterization is that due to Daniel and Hauswirth, independently, one of the other, that a minimal surface in H2 cross R foliated by horosphere in parallel planes must be the generalized catenoid. By the way, I always refer this generalized catenoid as Daniel's surface. So if I said Daniel's surface, I'm meaning this generalized catenoid. Okay, so I'm interested in this, what can be called the Dirichlet problem at infinity. So you prescribe a boundary at infinity when you can have a solution. The simplest situation is you consider just one curve gamma, which is a vertical graph over the ideal boundary. In this case, Nelly and Rosenberg, they prove that there exists a unique minimal disk whose ideal boundary is this curve gamma. So that means that if you consider C as the space of these horizontal curves, and D the space of minimal disk, so the natural projection that projects a disk in its boundary is a diffeomorphism. So the next step that we are interested in is what happens if you consider two curves at infinity. So you consider two connected, not simply connected, but two connected minimal surfaces. So I'm going to denote Z as these pairs of curves. Well, I will assume along all the talk that the curves are of class C2 alpha at least. And then I consider the space of minimal annuli projecting over this space, so that the boundary is a curve in this space Z. So we have these results. First, that if you have an annulus and the boundary of the annulus is a C2 alpha curve, which is a graph, then the ends of the annulus are graphs, which is not trivial. I mean, I have to say that this result, which is in the paper that I mentioned at the beginning, is nothing but a refinement of a result by Colin, Hauswirth, and Rosenberg. They proved the same thing when you have an annular end, which is contained in a slab. So we realized that the argument can be modified in such a way that you only need that the boundary curve is a graph over the ideal boundary of H2 and some regularity, at least C2 alpha. Well, probably could be reduced to C1, but with C2 alpha you are safe. Oh. So the other thing which is important is that if you have a minimal annulus so that the boundary has some kind of regularity, you can extend the annulus with the same regularity. That means that if the ideal boundary has class C3, you can extend your annulus as an annulus of class C3 as an annulus with boundary, which is also important if you want to do some computations along the boundary. And so, as well, C is a Banach manifold. This is straightforward. And something which is not so clear is that the space of minimal annuli whose boundary is are in C is also a Banach submanifold of the space of all minimal annuli. And moreover, the natural projection that I'm going to divide in P plus and P minus. P plus means the top curve of the boundary, and P minus the bottom curve of the boundary. So this projection is a Fredholm of index 0. Unfortunately, it's not like in the case of minimal disk. So this projection, pi, is not onto. What we have proved in the paper is that P plus and P minus, independently, they are onto. But both together, no. And the sample for this is very simple. So I'm going to write the curves in this way, so as graphs over the ideal boundary. So the first theorem is that if you have two curves, it's a non-existent result. If you have two curves so that the distance, the point-wise distance between 2 points in the same vertical is more than pi, this quantity is bigger than pi, then you cannot find an annulus bounded by these curves. Well, this is a corollary of something more general, but this is quite simple to prove. So imagine that you have two curves like the one in the lemma, well, in the theorem, sorry. So you have one curve here and another curve here. And imagine that you have an annulus that spans this boundary. So I'm going to consider these curves. So I consider two vertical segments and the corresponding pieces in gamma plus and gamma minus joining these two vertical segments. So if you start, and then using Koskounuser result, this is a tall curve because the assumption, so you can find a solution of this asymptotic plateau problem, and it's an area minimizing disk. So when the distance between the segments, when these segments, the distance goes to 0, what you have is just a segment at infinity that doesn't touch your surface. And then you start to open this distance, or you open this angle here, this angle alpha, from 0 at the beginning to pi, to 2 pi, I mean to the opposite segment, the segment in the opposite side. And then if you see this configuration or this picture from one side, what you see is here a curve, here another curve, and you start here with this vertical segment, and then you are moving the segment along this until here. And what is the limit of this family of area minimizing disk as the angle alpha goes to 2 pi when you arrive to the antipodal segment in the cylinder? The limit consists of the Nelly-Rosenberg disk on the top, Nelly-Rosenberg disk on the bottom, and this segment. But as you have a continuous family of minimal disk, this continuous family foliates all the space between this segment. So you have the different solutions are, well, a ball like this, I don't know. But foliates all the space between these two disks. At some point, they have to touch your annulus. And by the maximum principle, you arrive to a contradiction. So this contradiction proves that there are no annuli with this property. But it's even worse because, well, then you see that in general, when you start with a pair of curves and you separate them too much, and this too much is precisely pi, you don't have an example, which in some sense is something similar or mimics the behavior of the curves in the Euclidean space. When you can start with two arcs, if they are very close, you have a solution, you have an annulus, and then you start to separate them, and the surface disappears. So, but even near, so as close as you want to curves where you know that there are examples, there are no examples. And the theorem is like this, is this. So you consider two curves. Just to simplify, you can imagine two planes forming some angle, and you cut the ideal boundary of A is 2 cross R, and then you get two ellipses like the ones in the picture. And the angle can be very small. So these curves, you can find as close as you want to two parallel curves that you know that there are examples. You have these rotationally invariant catenoids. As close as you want to these curves, you can find one of these configurations. Then there are no annuli bounded by these curves. And the idea is also very simple. It's just a consequence of the moving plane method. So imagine that you have this boundary, and you have a minimal annulus that spans this configuration. Then you consider vertical planes, totally geodesic planes, and then you start to reflect from this point and use Alexandrov reflection. You can start, because when you consider one of these planes here, and you reflect, due to the angle, the reflection doesn't touch the other part of the annulus. And then you can start. And this kind of arguments is like when you eat corns. When you start, once you start, you can not end. So, but then you go and you start to reflect until the reflected touches the other part, because you are assuming that you have an annulus. And then you arrive to a contradiction by the maximum principle. So, also it's quite clear that the projection, this projection is not proper. And the example, well, it's better to illustrate it with a picture. You consider I have drawn just half a catenoid, because it's easier to see. And then you apply to this half catenoid horizontal dilation in any direction. What you get is something which has exactly the same boundary. So that means that for a particular fixed pair of parallel circumferences, you have a two-dimensional family of annuli projecting over. So this is pretty far from being, well, a diffeomorphism, but also from being proper, because what is the limit when you apply dilations of ratio bigger and bigger? What is the limit when the ratio lambda of this dilation goes to infinity? So the limit, it consists of two horizontal disks joined by a segment at infinity. Because the neck, the effect of these dilations, when you horizontally dilate the catenoid, the neck at the end converges to a segment, a vertical segment joining the two circumferences. Okay, so what we can expect? So the question then is, under what assumptions we can expect compactness in the space of annuli? So what are the hypotheses that you have to add to a family of annulus to guarantee that you have a limit? Well, we know that if we have a family of annuli like the ones we are considering, we have that there is a cylinder, solid cylinder in H2 cross R, so that outside this cylinder, what you see consists of two vertical graphs. So the question is that we are considering three cases. The cases of the first one is when this you can consider like a uniform cylinder. So you have a universal cylinder, so that outside this cylinder all the annuli are graphs. But this is not always the case. For instance, the picture that I showed you before, this cylinder can have a fixed radio but escape to infinity. This is the second case. And the third case is the case that the radius of the cylinder goes to infinity, which is the worst one. So what can we say in these three cases? Well, the simplest one is the case one. So imagine that we have a family of annuli that converges. In this case, the family, up to a subsequence converges to an annulus. And the reason is this. So recall that we have a family of annuli, so that outside a fixed cylinder, all of them are graphs. So using Ascoli-Arcela, what you can prove is that outside this cylinder, you have convergence, because everything is smooth and is bounded, the geometry is bounded. So outside the cylinder, you have convergence to minimal graphs, because limit of minimal graphs are again minimal graphs. So if something wrong happened, this something wrong must happen inside the cylinder. So, but observe that if you consider the Mn is the part of the annuli which is inside the cylinder, all these cylinders, all these annuli satisfy that the boundary is the length is uniformly bounded, because the boundary consists is part of the graph, is the boundary of the graph, the interior boundary of the graph. As you have convergence of the graphs, then you have that this length is uniformly bounded. Observe also that the set that I'm going to call C, where the area of this annuli blow up, must be inside this cylinder, because outside the cylinder we have a smooth convergence and blah, blah, blah. Okay, so I'm going to use this theorem by Brian White, saying that in these circumstances, which is precisely the ones that I have, then this set Z obeys the same maximum principles that hold for properly embedded minimal surfaces. So that means that you have in H2 cross R, you have the cylinder, and you have your set Z, who knows what is the shape, but is inside this cylinder. So what I'm going to do is, as is inside the cylinder, I consider one point in this set. I'm assuming that this set is not empty. Then I consider a minimal catenoid which is outside the cylinder, so that the symmetry plane is at the same height at this point here. And then I start to move the height of the catenoid from H to 0. The limit of the family consists of a double copy of a horizontal disk. So that means that at some moment, this catenoid, a member of the family must touch Z. But using White's theorem, then by the maximum principle, Z must coincide with this catenoid, which is absurd because the catenoid is not contained in the cylinder. So, consequence of this set Z is empty. And then I use this theorem, again by Brian White, saying that in these circumstances, I have, you need bounds about the area that I have because the set Z is empty, and also bounds about the genus. But in my case, everything is quite simple because all the members of the family are annuli. Then you have either one of these two things. Either you have convergence to a surface sigma, which is with multiplicity 1, or you have convergence outside a discrete set with a higher multiplicity greater than 1. But as outside the cylinder you have convergence with multiplicity 1, then the convergence must be smooth with multiplicity 1 everywhere. And then you have a good limit. and that proves the theorem. So that's the proof in case 1. What happens in case 2? Well, in case 2, in this case, the family of radii is independent of, so you have a cylinder of a fixed radius, but the center of the cylinder, the axis of the cylinder moves to the ideal boundary. So what happens in this case? What is happening is that the limit is like in the case of the catenary. It consists of two minimal disks joined by a segment at infinity. So, but what is important is that what you see when the sequence, so the neck of the annuli is disappearing at infinity. But what you see at infinity is a catenoid forming. Because what is saying, the second part of the theorem says that if you translate, you have this neck escaping at infinity. So you translate the neck to the origin and take a limit of this. The limit is a rotationally invariant catenoid. In particular, what we have is this. If you are assuming that the neck is escaping to the segment bounded by these 2 points, the height between these 2 points where the neck is escaping must be less than pi. Okay, the proof of this case is simple again. So now you consider this domain lambda n. And now what happens is that lambda n converges. You have a family of cylinder, so with the same radius that is escaping at infinity. So the limit of this domain is the whole H2. So by Ascoli-Arcelà, outside a horosphere, you have convergence to the graphs. And then, if you call sigma n to this translation, what happens is that if you apply sigma n, so you are taking this neck, which is escaping to infinity, and you translate to the origin. So this new sequence is in the condition of the case 1. Because you are taking this cylinder and translating it to the origin. And then you apply case 1 and you get a limit. But when you have any curve and you apply a sequence of dilation so that the ratio goes to infinity, which is the case, the limit of the curve that you get at infinity is circumference. Because these translations have this effect over the boundary curves at infinity. This has this flattering space. So you have, using case 1, you have a good limit, and using Nelly's IR2 exam characterization, you have a minimal annulus bounded by 2 cycles in parallel planes. Then that means that is a catenoid. Okay, so in particular, the difference of the heights must be less than pi. Well, I'm going to escape this part. Okay, so finally, what happens in the final case, in case 3? Oops. In case 3, the limit that you have the case 3 is when the radius of the cylinder diverges to infinity. So you have a family of annuli so that the size of the neck grows and grows and grows. So what you have is that what you see in the previous case, what you see at infinity is a catenoid forming. Now what you see at infinity is a general catenoid forming. I mean, a Daniel's example forming at infinity. And this is the behavior. So that means that these two examples, catenoids and generalized catenoids, characterize the asymptotic limit of this annuli at infinity. Well, finally, I would like to finish saying what can we say about existence. So the simplest existence result that we can give is this one. Imagine that you have a finite group of isometries in H2 cross R so that they live invariant one of the catenoids, but in addition, you assume that the space J naught is the space of non-decaying Jacobi fields of these catenoids is not preserved. For a catenoid, as the projection is not diffeomorphism, so you have this, in particular, for any catenoid, this space has dimension 2. And so the two kind of example of groups that we have in mind is especially this one, which is the most interesting, rotations around a vertical axis, or this C2 times C2 generated by two motions, a reflection across a vertical plane and a rotation around a horizontal line. So then what we can prove is that for any G invariant curve, you can have a G invariant annulus spanned by this curve. And the idea, I'm not going to enter in details, is you consider now the projection. Instead of the general projection, the projection restricted to the space of G invariant curves. So this projection now is proper. Is Fredholm, index 0, and proper, so you have a well-defined degree. But as G doesn't preserve the space of Jacobi fields, so the projection around the catenoid is a diffeomorphism when you restrict it to the space of G invariant annuli. So in this at manifold, the projection is 1-to-1 near the catenoid, and it has a well-defined degree, so the degree must be 1 everywhere. And so what you have a map of degree, Fredholm, index 0, degree 1 is on 2. And that's the idea of the proof. And I think it's a good point to stop. Thank you very much for your attention.